This sixth quantum mechanics lecture may be a little long because we've got quite a bit of ground to cover. We're going to look into wave functions and then how to build one for particle in a box, which is a sort of thought experiment or simplified model of quantum mechanics, and then do some calculations on it. So we've already covered things like quantum states and the Schrödinger equation. Now we're going to add in a little bit more detail that allows us to do some actual calculations with it. So a quick recap. The idea of particles and waves in quantum mechanics is really important because we're often told that things can be particles and waves at the same time. I don't particularly like that description. I prefer to think of it as they can be described as particles and they can be described as waves depending on the circumstance. It's slightly easier to get your head around that way rather than imagining this weirdly paraconsistent idea of them being two different things at once. Think of electrons as being described by these concepts. So a particle, for instance, has a definite location. It is here. We have an x, a y, a z coordinate, a definite direction to its velocity. And it's modelled as an infinitesimal point. So it's not like a ball that has some kind of extent. It has no dimension to it. It is a complete point particle. Waves, on the other hand, are a lot more spread out. They're a little bit more abstract to think about. A wave can build up, decay, build up again. And so it can be said to be more here and less over there. But generally speaking, it does not have a definite location. But we can describe it as a function that changes over space and time. So instead of saying that it is here, we can describe the wave as a mathematical function instead. And waves in quantum mechanics will relate to probability. So a wave function will only represent a probability amplitude. This will be familiar if you got your head around the idea of vectors that we started with. Because probability amplitudes, these wave functions, can be negative and they can also be complex. So we can't get a minus 50% chance of something happening and we can't get an I chance of something happening, for instance. Neither of those concepts make sense. Probability's got to be a positive real number. So to do that, we need to square our wave function, and that gets us a probability function instead. So the wave can go up and down, but we have to square whatever that value is to get actual probability. And we can say that a particle described by a wave function is more likely to be here, less likely to be here. So for quantum mechanics, wave functions can't just be any old function. We can't just throw x squared plus 4x or whatever at the wall. We need to satisfy certain criteria. The first one is that it's got to be single valued. So let's say if we had a function that did this, it would be quite an unusual function, but it can't possibly work because look at this point here. There are 3 values for it. So if there's 3 values for the wave function, 3 values for the wave function squared, 3 values of probability. That doesn't make any sense. There's got to be 1 value of probability. So here would be fine. That value squared would be the probability of being fine. Here wouldn't work. It also must be non-zero everywhere. Bit of a complicated one, but it means that just 0 as a wave function isn't acceptable. It's a very basic requirement, but if we could just plug 0 into here, a lot of things would break. So we can't have a wave function that is 0 everywhere. It must have some finite values at some point. So that would be a nice, smooth looking wave function there. It's also got to be smooth and continuous. So we can't suddenly have a break. You can often see mathematical functions that do that, for instance. They might just break and then restart somewhere else. That's actually valid. You can describe that in the language of mathematics. You can't turn them into wave functions. And there can't be sudden dips or changes like that. So none of that can work as a wave function. It's all got to be smooth. And finally, and this is a more technical definition, it's got to be normalizable. So this in short means that the total probability has got to be 100%. We covered that in the vector type model that we looked at earlier, where all of those coefficients squared had to equal 1. Well, here, when we square the wave function, it's got to be able to be scaled to 1. And generally speaking, that just means we have to close the function off. If this drops down to nearly nothing here, then the area under this curve, which is sort of related to probability, can be scaled to 1. What we can't do is have a function that just shoots off like that, because suddenly the area under this curve can spiral out to infinity and we can't scale it down. So whatever this function is, we've got to be able to scale total probability to 100%. Right. So with those in mind, let's have a look at a particle model and what are the constraints on a wave function this could have. So we might think of a box like in 3 dimensions here, and we could put an object in it, but that's quite complicated. I mean, we're chemists, we're mathematically illiterate at the best of times, so we want to simplify it down just a bit. So let's remove a dimension, let's get rid of Z. And we have, instead of a 3D box, we've got a 2D box. Still a bit complicated, that's 2 things to think about, so let's just drop it to 1 dimension. There's actually nothing technically wrong with this. It's hard to visualize dropping something into a box, but all you need to know is there's a particle in here and it can move back and forward freely. If it makes it more comfortable, think of this like a wire. This is a wire with an electron to do with electricity going back and forward with it. Or, and it simplifies a little bit, but it's a good model, this multiple conjugated bond here. That's sort of a one-dimensional box. It has a length and electrons can zoom back and forward along it quite easily. So we do have 1D boxes in reality. We drop particles in and they can just move back and forward completely freely. So the wave function for this to describe where we could possibly find a particle must satisfy various constraints of the box. Outside the box, the particle cannot appear. This is a brick wall that it cannot penetrate. It's an infinitely high potential. The particle cannot escape it. So what must happen is that here and here, the value of the wave function must be 0. No matter what, it can do what it likes inside, but as long as it's 0 there, we can have a satisfactory wave function. So the basic wave function that will satisfy all of those constraints, it's a mathematical object that works really well, and it will be an eigenfunction of the Schrödinger equation, is sine of x. That gets us the right shape. You can try cosine of x if you like, but what you'll realize is if you do cosine of 0, that is equal to 1. So at the edges of the box at x equals 0, the wave function actually has a value. That can't happen, it must be 0. So we can't use cosine, we can only use sine. But that's not the end of the story, because sine x just goes along arbitrarily. What happens at the other side? Well, in this case, we can change it slightly and put x over L. And that takes into account the length of the box. Now, if x equals 0, sine of x equals 0 is going to be 0. Great, the wave function will be 0. And if x equals L at this point, well, x is L, L divided by L is 1. Sine of 1 is, well, we'll get back to it. But at least now, we know that we've got a ratio along the box that we can do. So let's solve that problem by adding in pi. Here, if x equals L, then x over L equals 1. Multiply it by pi, that must equal pi. And sine of pi is 0. Pi being the equivalent of 180 degrees in a sine function. So we know that no matter what, out of this equation, at the edges of the box, the wave will be 0. Great. What else can we add to this? We can add n. So this, providing it's an integer number, so we can add 1, 2, 3, 4, etc. We can actually change the shape and size of that wave. We can fit more than one wave into the box. It doesn't have to be just up and down. It can go up and then down and back up again, and it can do further shapes later. Draw those out in a moment. And finally, we want to normalize it. So this A factor here will not cover right now what that value is, but it will be able to scale the wave function up and down so that the total probability described by it adds to 1. It won't be too large, it won't be too small. So normally most wave functions have this in. There will be a factor at the very beginning that is a normalization constant. It simply scales the wave function. So let's draw what they look like. If we plot this out and do this by hand, do it in Wolfram Alpha, do it in Excel, do it in Python, whatever you want to do, you can plot this out. And you will find that the wave functions look a bit like this. So n equals 1, it is a smooth curve. It actually keeps going here, but that's outside the constraints of the box. We can ignore it. As long as it's 0 here, we don't mind. If we increase this n to 2, we actually shorten the wavelength a bit. Do this with a calculator. You realize if you stick a coefficient in front of the x in sine x like that, it will change its wavelength. So we actually get a shape like that. It's a shorter wavelength. Again, it would keep going, but we don't really care about that. We can ramp it up even further. N equals 3. We'll get something like that. And n equals 4. Getting quite a tight wavelength now. It can keep going like that. And we can keep ramping n up effectively to infinity. I'll stick a couple of extra resources for showing you how that works in terms of harmonics. And so mapping this from wave function to probability, let's just pick n equals 2 because it's a nice looking one. Well, here we've got the maximum value, here the minimum value, but that's negative. We can't have a negative probability. So let's square it. Here this maximum value squared is going to still be the maximum. Here the minimum squared is going to become a positive number. And at the edges, 0 times 0, 0 squared is still 0. And at this bit in the middle, which we call a node, where it crosses the x-axis from positive to negative, it's still 0. So 0 times 0 is still 0. And if we join that up, we get a plot that looks a little bit like this. And this is our probability function. The top one being the probability amplitude, the bottom one being probability itself. So we can see that here the particle is very likely to appear. Here the particles are very likely to appear. Here there's actually 0% chance that the particle can appear at all. So if we measured it, we will never find it at that exact halfway point, which raises some interesting ideas about, well, if it's over here, how does it get to that side without passing through the middle? Questions like that are really complicated, and there isn't really one satisfactory answer. It's quite an advanced bit of quantum mechanics known as the measurement problem. Mostly we're not going to care too much about that. It's very in-depth and depends on your viewpoint and your interpretation of it. We're just interested in the equations right now. So let's have a look at all the calculations that we've built up so far. There are a few of them, but let's break them down. Here we've got the Schrödinger equation. So that's our deceptively simple version of it, simply 4 letters and an equal sign. We know that the H, the Hamiltonian operator, breaks down into kinetic and potential energy. Now, luckily for us, in the particle in a box model, there is no potential. Inside the box, the potential energy is 0. So effectively, we can ignore potential energy entirely. We will not come back to potential energy until we do at least the harmonic oscillator a little later on. And we also know that the wave function must be this. This is the one we've just built. But we can do a little bit of simplification there. And I would encourage you to do this kind of simplification if you ever do any maths or working out yourself. These are all constants, and we would have to draw a lot of ink and use a lot of ink and draw a lot of figures to write that out each time. So let's just simplify. Let's get rid of it. Let's take that n pi over L and just say that it's A. Now we've got a much more simplified and streamlined wave function. A little easier to do the following maths with. So if we assemble all of that, we take what h is equal to, well, it's equal to t, we know what t is equal to, we know what psi is equal to, and put it all into one thing, we get this. And if you think you can go ahead and do that, do stop and do it. It is simply deriving a sine function and then multiplying it by some stuff. If you know how to do that, great. If not, I'm going to rattle through it now. Normally I would take a bit more time over this, but we're in a video format. Let's go through it reasonably quickly. So the first thing we are going to do is we are going to take that capital A outside of the d by dx part, because we're not going to derive that. We only want to derive parts that have a function of x in there. So let's do that. Let's take a derivative of sine. And if you take a derivative of sine, you get cosine. And anything here hops out. Any coefficient in front of the x hops out of the function when we take a derivative of it. We can put that over there to get rid of it, because we just want to take a d by dx of this cosine now. And if we do that, we get a sine x again, specifically negative. So we've cycled back around to sine, but negative. We can tidy that up a bit. We can bring the a to a squared, and we can multiply the negative by a negative to get positive. That's a good sign. Our energy here is going to be positive. Good. So we can bring that a back across and realize, well, this is our original function. Great, this is a really positive sign, because we can get rid of that and just simply write psi. And this is proven that this is an eigenfunction of the operator. It's working. Great. So this also now tells us what E is equal to, what the energy is going to be equal to, because we can simply cross off these two psi's and realize that a squared times h bar squared over 2m equals E. Can we do better than that? Can we tidy it up a little bit? Well, of course we can. We have to get rid of that a again and put back in these previous values that we had. So a is equal to n pi over L, a squared is n squared, pi squared over L squared. We can substitute that all in as well. Tidy it up just a little bit, and then there's our expression for energy. Including a pi squared is a bit awkward though, so let's notice that here is Planck's constant but being reduced. So what is the reduced Planck's constant? It's h bar is equal to h over 2 pi. So h bar squared is h squared over 4 pi squared. Let's substitute that back in. And here we've got pi squareds that are going to cancel. And here we have a final expression for energy. N, that's what we would call a quantum number. That was giving us the different shapes of the wave, squared, Planck's constant, squared, the mass of the particle, and the length of the box. So that is telling us that energy is going to be proportional to that n squared, but inversely proportional to the length squared. So if we lengthened the box, the energy would drop. If we shortened the box, the energy would go up. And if we increase n, the energy goes up. If we decrease n, the energy goes down. And that should make sense, because if you do those operations, you're either lengthening or shortening the wavelength. And you should know that wavelength is proportional to the energy. We should have covered that in spectroscopy. So I'm going to do a quick dimensional analysis of that final expression to prove that it definitely works. We have on the top Planck's constant squared and a mass and a length. So Planck's constant is measured in joule seconds. Let's break that up to joules being kilogram meters squared per second. Same dimensions of E equals mv squared, or kinetic energy being half mv squared, for instance, and multiply that by seconds. So let's multiply the seconds. So we've got seconds to the -1. Let's do those squaring things. So we've got kilogram squared meters to the 4, seconds to the power of -2 again, and meters squared underneath. We can get rid of 2 meters there by dividing through by the meters squared. And we've now got kilograms squared on the top and kilograms on the bottom. We can get rid of it. There we go. Our energy is in kilogram meters squared per second. That is joules. That is a unit of energy. Fantastic. This works. This is a value of energy. And it's all popped out of some very quite basic things. All we needed to know was momentum to build a kinetic energy operator, and all we needed to know was some constraints for what a wave should be. And look, we've magically managed to get something that can give us energy. So if you couldn't necessarily follow that, there will be more material for you to follow more slowly. Certainly try it yourself on various versions of that equation. It's something to get your head around. It's a really nice derivation to get used to. So let's do the recap. So wave functions, these are mathematical functions, and we are describing quantum states with them. All of those squiggles and sine functions, those are individual quantum states. And we can make a simple wave function from sine x. We have to put a few more bits in to make it fit the box properly, but we can still have a quite simple function. And then when we apply the operator, we can get energy out of it. So all of those quantum states have an associated energy, and we can get them simply by throwing the kinetic energy operator at it and doing a little bit of maths.